Now, consider the exact same problem as before, but assume that we know the value delta I for all I ranging from 1 to m, that is, for each observation. We know that if delta I equals 0, the observation comes from the first Gaussian, the one with parameter θ1, and otherwise the observation comes from the second Gaussian, the one with parameter θ2. In the case where we know delta I, the corresponding log likelihood, called the complete log likelihood, writes as in equation 65-66. The first term is the same as before, but there is an extra term corresponding to the random variable delta I, which is a Bernoulli variable. The second term corresponds to the log probability of having delta I equal to 0 or 1, which depends on the probability pi, the probability that delta equals 1. You can obtain this exact expression by writing the joint distribution of x delta and the corresponding log likelihood, which is exactly the complete log likelihood. Since we do not know the values delta I, we replace them by their expected values, which are defined as gamma I of theta. In order to find the parameters θ1, θ2, and pi, we're going to maximize the complete log likelihood of the problem, see equations 65-66, where we replace the delta I by the expected values gamma I of theta. Then we will solve this problem iteratively by maximizing the complete log likelihood along θ1, θ2, and pi. Then we will update the gamma I of theta and repeat the procedure. This algorithm is called an expectation maximization algorithm, since we iteratively compute expectations and maximize the resulting quantities. Let us write explicitly the EM algorithm for this problem. We first initialize the parameter values θ1 hat, θ2 hat, and pi hat. Then the expectation step consists in computing the gamma I defined in the previous slide as the expectation of delta I given the current parameters and the data set. Indeed, note that gamma I is exactly the probability that the data point xi has been generated via the second Gaussian distribution. Once these gammas have been computed, we can inject them inside the complete log likelihood to replace the values delta I. Once this has been done, it is easy to maximize the resulting log likelihood with respect to θ1, θ2, and pi. The result of this maximization is given in equation 69-71. Note that the result here is nothing but weighted mean for μ1 and μ2 and weighted variance for sigma 1 square and sigma 2 square, where the weights are the gamma I hat. For example, the points that contribute the most to the expression of μ1 are the points for which gamma I hat is close to 0, which corresponds to points likely to belong to the first Gaussian distribution. So quite logically, to compute the mean of the first Gaussian distribution, we just compute the weighted mean of all points where the weights, the gamma I hat, correspond to the probability that a point belongs to the first Gaussian distribution. It's exactly the same for the other parameters. The expectation and maximization steps are then repeated until some convergence is reached. The final values are the final estimation for parameters θ1, θ2, and pi.